Hello, welcome back. We were discussing continuity. In the last video, we have seen continuity at a point and also continuity test. And today we are going to discuss rules of continuity, which includes continuity of algebraic combinations, as a result, continuity of polynomials and rational functions, and also continuity of composite functions. I am following the textbook Calculus and Analytic Geometry, 9th edition by G.B. Thomas and R.L. Finney. Chapter 1 Limits and Continuity and Section 1.5 Continuity. Okay, we can go to the video. Rules of continuity. As we have seen in the case of a limit, sum rule, difference rule, product rule, constant multiple rule, quotient rule and a power rule hold for continuous functions also. We can see the first theorem, continuity of algebraic combinations. Continuity of algebraic combination says that if we have two functions f and g that is continuous at x is equal to c, then sum of these two functions, difference of these two functions, product, constant multiple, quotient and power of these functions will also be continuous at x is equal to c. C. If functions f and g are continuous at x is equal to c, then the following functions are continuous at x is equal to c. First one, f plus g and f minus g. If we take two functions f is equal to x, f of x is equal to x and g of x is equal to some constant function 2, f of x is equal to x, the identity function which is continuous. You can check here, the graph is f of x equal to x will be like a f of x is equal to x. This is continuous and a constant function. Say g of x is equal to some 2. 1, 2. These two functions are continuous. Then f plus g is equal to x plus 2. X plus 2. So the graph will be like a 2 unit from 0 origin. X plus 2. This function is also continuous. Like that we can say x minus 2. That will be like here. If this is 2, the function will graph will be this x minus 2. This is also continuous. Second one, f into g. If f and g are continuous at x is equal to c, then f into g. Here we can see f is equal to x, g is equal to 2. Then f into g is equal to 2 into x. The graph will be like at 1 y is 2, at 2 y is 4, like that. The graph will be like this. This is also continuous. Third one, k into f, where k is any number. If f is continuous at x is equal to c, then k into f, scalar multiple, is also continuous. You can say here we take g of x is equal to 2. If f is continuous, then 2f is also continuous, or we can say minus x is also continuous. Minus x will be like this. This graph is also continuous. Fourth one, f by g, provided g of c not equal to 0. If f and g are continuous at c and g of c not equal to 0, then f by g is also continuous. Here we can say 1 by 2x is also continuous. The graph will be like this. Here at 0, value is 0. At 1, y is 1 by 2. At 2, y is 1. Like that. Fifth one, f of x the whole power m by n. provided f of x the whole power m by n is defined on an open interval containing c and m and n are integers. Here we can say f is equal to x. We can take m equal to 1 and n equal to 2. F of x whole power m by n equal to x raised to 1 by 2. Here that is root x. Here f is continuous, then the function root x will also be continuous. You know the graph of root x. This is the theorem continuity of algebraic combinations. That is, if functions f and g are continuous at x is equal to c, then the following functions are continuous at x is equal to c. F plus g and f minus g. That is sum and difference of these two functions. Second one, f into g. That is product of these two functions. Third one, k into f. That is scalar multiple of a continuous function is also continuous. Fourth one, f by g provided g of c not equal to 0. That is quotient of two continuous functions is also continuous, and we have one condition, the denominator is different from 0. And fifth one, f of x the whole power m by n. M and n are integers, and also f of x the whole power m by n is defined on an open interval containing x is equal to c. As a result of this theorem, we can say polynomial functions and rational functions are also continuous. Polynomial functions are of the form a1x raised to n plus a2x raised to n minus 1 plus etc. plus some a. Or we can take the second degree polynomial some 3x square plus 2x plus 5. Here see f of x is equal to x is the identity function which is continuous. So x square is also continuous. X square is equal to, we can say x into x using the second property, or we can say x raised to 2 by 1 using the fifth property. You can say that x square is continuous. Therefore 3x square is also continuous. This is a scalar multiple of continuous function which is also continuous, third property. Then like that 2x is continuous and 5 is the constant function which is also continuous. Here the sum is also continuous. We can extend the sum of two functions to finite number of functions. So the sum is also continuous. Like that we can say that polynomial functions are continuous. Like that rational functions are also continuous. Rational functions are of the form f of x by g of x. F of x and g of x are polynomials. We have seen that polynomial functions are continuous. Therefore, by fourth property, quotient rule, the rational functions are continuous provided g of c not equal to 0. Okay, we can see the theorem. Theorem, continuity of polynomials and rational functions. Every polynomial is continuous at every point of the real line, and every rational function is continuous at every point where its denominator is different from 0. We can see example. The function f of x is equal to x raised to 4 plus 20. This is a polynomial function which is continuous. And g of x is equal to 5x into x minus 2. This is also a polynomial function, that is 5x square minus 10x. This is also continuous. Also, the function r of x is equal to f of x by g of x, a rational function, which is equal to x raised to 4 plus 20 by 5x into x minus 2. Here, this is the rational function, and here the denominator is 0 when x is equal to 0 and x is equal to 2. So except these 2 points, the function is continuous, or we can say r of x is continuous at every point except x is equal to 0 and x is equal to 2. At these 2 points, the denominator becomes 0. See another example, mod x, continuity of f of x is equal to mod x. The function mod x, f of x is equal to mod x. We can define it by which is equal to x when x greater than 0, 0 when x is equal to 0, minus x if x less than 0. Or we can draw mod x by f of x is equal to x minus x. We can check the continuity. When x greater than 0, we can say f of x is equal to x, a polynomial, or this is an identity function. Clearly, it is continuous. When x less than 0, f of x is equal to minus x, which is also a polynomial function, or minus 1 into x is continuous. At x is equal to 0, limit x tending to 0, f of x is equal to, here when x is tending to 0, the function f of x is also tending to 0. And f of 0 is also equal to, that is, the limit is equal to the function value. Therefore, at x is equal to 0, f of x is continuous. So, we can say that f of x is equal to mod x is continuous at every point. Next example, continuity of trigonometric functions. That is sin x, cos x, tan x, etc. Sin x, f of x is equal to sin x, and g of x is equal to cos x, is always continuous at every value of x. Therefore, their quotients, that is tan x is equal to sin x by cos x, will be continuous. Cot x is equal to cos x by sin x is also continuous. Sec x is equal to 1 by cos x is also continuous, and cosec x is equal to 1 by sin x is also continuous. Next, we can see the continuity of compositions. Theorem, continuity of compositions. If we have two functions f of x and g of x, and f is continuous at c and g of x is continuous at f of c, then g composite f is continuous at c. We can say if we have two functions f of x and g of x, f of x is continuous at c and g of x is continuous at f of c, then the function g composite f is continuous at c. If f is continuous at c and g is continuous at f of c, then g composite f is continuous at c. We can see some examples. Example, the functions y equal to root x, y equal to root of x square minus 2x minus 5. Third one, y equal to x cos x raised to 2 by 3 by 1 plus x raised to 4. D, y equal to modulus of x minus 2 by x square minus 2. All these functions are continuous everywhere on their respective domains. See first one, y equal to root x, or we can write y equal to x raised to 1 by 2. Here x is continuous, therefore by power rule x raised to 1 by 2 is also continuous. That is, a rational power of a continuous function is continuous. Next, y equal to root of x square minus 2x minus 5. Take f of x is equal to x square minus 2x minus 5. Clearly, this is a polynomial function which is continuous. Therefore, f of x raised to 1 by 2. That is, rational power of a continuous function is continuous, is also continuous. Or we can say, take f of x is equal to x square minus 2x minus 5 and g of x is equal to root x. We have seen root x is continuous. F of x is also continuous. Therefore, g composite f is equal to root of g of f of x. It is equal to root of x square minus 2x minus 5. Is also continuous by composition. The composition rule can be extended to finite number of functions also. See y equal to x into cos x raised to 2 by 3 by 1 plus x raised to 4. Here consider cos x raised to 2 by 3. Take f of x is equal to x raised to 2 by 3 and g of x is equal to cos x. Cos x is continuous. X raised to 2 by 3 is also continuous. Therefore, g composite f is equal to cos x raised to 2 by 3 is also continuous. Here x is continuous. Therefore, x into cos x raised to 2 by 3 is also continuous. Now, see 1 plus x raised to 4 is also continuous. This is a polynomial function. Therefore, this quotient is also continuous. Here the denominator cannot be 0 in real life because x raised to 4 equal to minus 1 has no real solutions. So this function is continuous everywhere. Last one, y equal to mod x minus 2 by x square minus 2. Here take f of x is equal to x minus 2 by x square minus 2 and g of x is equal to mod x. So g composite f is equal to modulus of x minus 2 by x square minus 2. Here this is a rational function continuous and a modulus function is also continuous. We have seen this example. Therefore, their combination is also continuous. Next, we can see some exercises. At what points are the functions in the following exercise continuous? First one, y equal to 1 by x minus 2 minus 3x. Here 1 by x minus 2 is a rational function with the denominator is 0 at x is equal to 2. At x is equal to 2, this function will be discontinuous. Otherwise, this function is continuous. So, this function is continuous at all points except x is equal to 2. Second question, y equal to x plus 1 by x square minus 4x plus 3. Here the denominator is x square minus 4x plus 3. We can factorize it by x plus 1 by, here take product is equal to 3, sum is equal to minus 4. 3, 1, minus 3, minus 1. 3 into minus 1 equal to 3, minus 3 plus minus 1 is equal to minus 4. We can factorize this by x minus 3 into x minus 1. Here this is a rational function which is discontinuous at x is equal to 3 and x is equal to 1. So we can say this function is continuous everywhere except x is equal to 3 and x is equal to 1. Next question, y equal to mod x minus 1 plus sin x. Here we can see sin x as a trigonometric function which is continuous. Also mod x minus 1 is also continuous. We can say take f of x is equal to x minus 1 and g of x is equal to mod x. X minus 1 is a polynomial function continuous. Mod x is also continuous, we have seen. Therefore, g composite f is equal to mod x minus 1, also continuous. Therefore, continuous function plus continuous function, which is continuous. Therefore, this function is continuous in all x or everywhere. We can say it is continuous everywhere. Next question, y equal to cos x by x. Here cos x is continuous everywhere and x is also continuous. Here this is a rational function with the denominator is x, which is 0 when x is equal to 0. So we can say this function is continuous everywhere except x is equal to 0. Next one, cosec 2x. See, cosec x is equal to 1 by sin x, or cosec 2x is equal to 1 by sin 2x. This is continuous everywhere except sin 2x is equal to 0. What is the value of x for sin x is equal to 0? Sin x is equal to 0 for all x is equal to n pi. That is sin 0 is 0, sin pi is 0. You can see the graph. Sin x in the y coordinate is 0 here and at a 0 degree and also at a 180 degree. Then again it continues. Therefore, x is equal to n pi. Therefore, we can say sin 2x is equal to 0 when 2x is equal to n pi, or x is equal to n pi by 2. So, we can say cosec 2x is continuous everywhere except x is equal to n pi by 2, where n belongs to z. Next question, y equal to x into tan x by x square plus 1. Here x is continuous everywhere, x square plus 1 is also continuous everywhere. Here a denominator x square is equal to minus 1, for x is complex value. So for real valued function, we need not to check the denominator x square plus 1. Now see tan x. Tan x is equal to sin x by cos x. Continuous everywhere except cos x is equal to 0. Cos x is equal to 0 when cos x is equal to the x coordinate. Here x coordinate is 0 at the angle pi by 2, 3 pi by 2, again 5 pi by 2, etc. That is x is equal to n pi by 2 for n is odd integer. Or odd integer, we can express it in the form 2n minus 1 pi by 2 or 2n plus 1 pi by 2. When n equal to 1, 2n minus 1 is pi by 2. When n equal to 2, 3 pi by 2, like that. Or 2n plus 1, when n equal to 0, 2n plus 1 is 1, like that. So we can say this function is continuous everywhere except x is equal to n pi by 2 or 2n minus 1 pi by 2 or 2n plus 1 pi by 2. You can say anything. If n pi by 2, n is odd integer. Or when 2n minus 1 pi by 2 or 2n plus 1 pi by 2, n is any integer. N belongs to z. Next question, y equal to root of 2x plus 3. Here clearly 2x plus 3 is continuous, root x is also continuous. Therefore, this function will be compositions. Take f of x is equal to 2x plus 3, g of x is equal to root x. Therefore, g composite f is equal to root of 2x plus 3. Continuous everywhere. So, this function is continuous everywhere or continuous in all x. Next question, y is equal to 2x minus 1 the whole raised to 1 by 3. Here we can say take f of x is equal to 2x minus 1, which is a polynomial function, continuous. Therefore, f of x the whole power 1 by 3. Rational power of continuous function, which is continuous everywhere. That is continuous in all x. Next, we have to discuss continuous extension to a point. We can see it in the next video. Also, we can discuss continuity on intervals. where we can see intermediate value property and intermediate value theorem. So see you in the next video. Till then, stay tuned. Bye bye.